Okay, so what we're doing today is switching a little bit and looking at a new coordinate system. That coordinate system is the normal tangential, or NT coordinate system. So far, we've covered position, velocity, acceleration, curvilinear motion, and defining motion in XY coordinates. So one of the things to remember as we go from coordinate 1 to coordinate 2, coordinate 3, is that the total velocity, total acceleration does not change. And so you have to remember how you're doing things. But just as a reminder, R is the position vector, and we're going to use that more in the next coordinate, so tomorrow's lecture, and it's xi, yj, zk. Y. Velocity is going to be more important today. And finally, acceleration, which is useful for both. So everything up until now, we've broken it up into essentially two coordinates. You really only look at xy, but you always have the mysterious third coordinate that we don't really talk about that often. But acceleration and all of the definitions you've used so far still hold true. So here's where things get a little bit weird. I have a particle that is traveling along a path, and I haven't shown that path, but let's take a look at that path here. The path sort of looks like this. And when dealing with a normal tangential coordinate system, I do not care about the location. I'm only going to define things with respect to magnitude. So S is magnitude, and it's always positive. So S is an increasing value that with time sort of starts at 0 and continues on, and you measure it in, say, meters, and you can have 100 meters, but it only is path dependent. So that's one of the tricky bits about this particular coordinate system. The other thing that's a little bit tricky is that we look at curvature. And as you're moving along that curvature, you have two things that are going to eventually be defined. It'll make a little bit more sense when we look at velocity because we don't care about position. But E sub n points in towards the center of curvature. And the idea is that on this curved path, as I'm traveling along, I can define circles. And every small bit of that curve can be defined by a different circle of a different radius. And each of those radii are going to be a function rho. I'll talk about that more later, but rho will be the important quantity that I look at. And out of this, I get this E sub n and E sub t. E sub n points in towards the center of curvature, and E sub t is tangential to the path. It's defined as following along the path, which, not coincidentally, is the same direction as the velocity. So if I have a path that looks like this, I have a velocity that is pointing in the same direction as E sub t. By definition, v does not have a normal component. If it had a normal component, it would be moving off the path. So v is equal to v E sub t, and E sub t is a vector, a unit vector pointing in the direction of motion. So I want to replace my ij because it might make more sense when dealing with certain types of coordinates. Now this is nice because at the very top, if you remember the beginning of the lecture, I had v, which was vx in the I direction, vy in the j direction, vz in the k direction. Now I just have one term. So it looks great. Ooh. But my acceleration is just going to be dv dt, of course. Same thing as before. And it will end up being v dot, which is equal to v dot E sub t plus v E sub t. Oh. Yeah. Dot. And as you kind of figured out already, when we dealt with ij coordinates, the unit vectors never change direction, nor do they change magnitude. They just follow along, and so they never do anything. But when you have a nt coordinate, you could have n flipped upwards, downwards, either way, and it also travels along the path. So E sub t is going to have a direction change, and when I do a time derivative, it's not 0. So what I want to do is what is the time rate of change of that unit vector E sub t? So I can start going back a little bit here. I really should not do position first, but okay. I can sort of define arc length. So as I'm traveling along that path, my s sub t, or s as a function of t, is going to change. It's increasing greater magnitude. It's always positive, super. I want to define a term which is going to be kappa as a function of s, which is going to sort of represent the bendiness of the path. So that's going to be the curvature of the path, and it's a function of the direction of the unit vector E sub t along the path. So as you travel along the path and as it changes, that rate, the magnitude of that rate of change is going to tell me something about curvature. So if I continue with this, and I substitute e's in here because I wanted e's, and I look at this sort of path, I can say that E sub t dot is equal to dE sub t ds ds dt. So my time rate of change of the particle unit vector is going to be a function of this curvature and a function of ds dt, which is v. So if I go back to my expression, substitute for E dot t with this expression, I end up with ds dt, which I should write out as v, v times dE dt ds. And I have a v already, so it's going to be v squared dEt ds. So now I have an acceleration term that doesn't look much better, but it's based on this curvature of the path. All right. Okay. Which is good. I can also say, well, E sub t is a function of s dotted with E sub t dotted or as a function of s is equal to 1. It's a unit vector. Dotting it with itself just gets you the magnitude. The magnitude is 1. Super. So if I do that, I can take the time rate of change of those terms. And time rate of change in this case ends up being dEt ds dotted with E sub t as a function of, I'm just going to say E sub t for now, plus dE sub t ds dotted with, actually it should be the other way around. Same thing, but boom, boom. 0. So if I take the dds of the upper equation and I do the chain rule across there, I get this relationship. So dEt ds dotted with Et plus Et dotted with dEt ds is equal to 0 because it's equal to 1. So as a function, it never changes. So out of that, if I take the derivative, calculate the terms, combine everything, I end up with 2e sub t dotted with dE sub t equals to 0, which implies E sub t is perpendicular to dEt ds. So I talked about unit vectors in lecture 3, and we did a derivation with a circle. Here's another derivation of the same idea showing that they're acting normal to each other. So the only thing is I can rewrite normal because they're both normal, or E sub n is normal. I can normalize that by the magnitude. I get 1, still 1. And the bottom term here is this kappa s, which was that curvature I defined just a few minutes ago. And the other term is the one I'm interested in. So E sub n is a function of the curvature and the time rate of change of that term. And it always points to the concave side of the path. Okay, so I got kappa s, I've got dETS, ds. I still haven't really written out my acceleration terms yet. So I'm actually going to do that here. If I take this expression, and I just rewrite it as kappa of s E sub n sub s equals the ET of s ds and keep all my vectors, I have that expression right there, and that gives me a function of one with respect to the other. And so I don't like using kappa. Kappa is curvature. I've got to describe it in a way that's kind of weird, but I would like a radius. And so if you remember at the very beginning of the sort of discussion on this, I showed you these rho terms. And the rho is the radius of the curvature, so the imaginary circle you draw to that point. And so kappa of s is equal to 1 over rho, which is the radius of curvature of the path. So I have from that an expression that's easier to sort of look at. So if I'm looking at a radius of curvature, it's easier for me to say 1 over rho, 1 over 1 meter sort of radius, as opposed to try to figure out what the curvature of the path at each point is. So if we go back, all the way back to this expression right here, I have v dot et, which I can keep. I'm happy with that. I have the second expression, which is a pain in the neck, because it's a time rate of change of E sub t with respect to s. But now I have a relationship for that times v squared. So if I go back and call this 1, whoop, my acceleration from 1 is equal to v dot, v dot magnitude E sub t plus v squared E sub n over rho. And that's a direct substitution for dEt ds. These types of substitutions, you don't have to worry about rederiving it. You should know where it's coming from. But again, the other sort of funny thing there is the transfer from E sub t to E sub n. So getting that derivative in.
Sorry. I'm a bit confused on how we transferred kappa s equals 1 over radius of curvature.
Oh, it's just definition for now. We'll just leave it as a definition. It's easier. I don't really want to go into the geometry. So you have all of that. You have that. Okay. I think we can work with that. That's enough. So that's my big equation. All of this work is really to get to that point. Now, one thing that I kind of throw in there is that if you have y as a function of x, you can get the radius of curvature. To be honest, you're never going to... All right, that looks better. That looks better. That looks better. Y is a function of x. There we go. All right. Rho of x is equal to 1 plus dy dx quantity squared, total quantity to the 3/2, divided by the magnitude of the second derivative of y with respect to x. This is not an equation you use very much. I think there may be one homework problem possibly that you use, but it takes no room on a crib sheet. So if you want it, you put it in there. Oh. So okay, so with polar coordinates, you can define 3 dimensions. I really have to stop doing 3 dimensions because it starts to get unnecessarily complex. But I, J, K, E, T, E, and E, B. So those are the unit vectors.
On the previous page, for the definition of E sub n, we do 1 over kappa.
Yeah.
Beside 1 over kappa, you do d E sub t s over ds, but on the left side it's over dt.
Where did I do that? Oh. Thank you. There we go. Thanks. So, I have my coordinate system here. I'm going to actually write this in the next steps only in 2 dimensions for the NT coordinates because, again, not really exciting in 3 dimensions. And I think I'm going to stop. For position, r is equal, I'm going to do this only in 2Ds. R is equal to rxi plus ryj. S, I've written in a different color because it's just a scalar. It's a magnitude. It's an increasing value. It has no direction in nt. Oop, oop. Velocity in Cartesian coordinates, two components, two vx, vy. In nt coordinates, only one term, magnitude of v in the et direction. Acceleration becomes more interesting because it now has a more complex form in nt. Acceleration x, acceleration y, component parts, acceleration t plus acceleration n in the t tangential and normal directions. This is kind of the important sort of thing for you to pull out from this. Aside from this, you sometimes use this to sort of say where you are along the path. You usually have it s as a function of x or time or something, and then you can do that. But generally, what you're more interested in are velocity and acceleration, the last two equations. And if you break it at the last two equations, you're going to have all of those terms there. They're describing the same thing. One thing that is really hard to sort of wrap your head around is that we're not describing new v or new a. We're describing new component values of each. So if you have the same projectile problem, acceleration is still g, acceleration is still g. The magnitude stays the same. But the component parts can change, and I'll show an example of that in a few seconds. Any questions on that? Oh, I'm missing the special cases. Actually, hold on. Okay. Say, for example, I have a car traveling along a path. It has a velocity and an acceleration. So there's that car. It's traveling along a straight path. Rho, in this case, is equal to infinity. And we're allowed to do that as engineers. So rho is equal to infinity. Acceleration is equal to v dot, which is dv dt. But normal acceleration, v squared over rho, is equal to 0. So if you have something moving in a straight line, its radius of curvature is infinite, and because it's got an infinite radius of curvature, it will have 0 normal acceleration. Yeah. So if I have a circular path, radius of rho, and I have a constant velocity, so v dot is equal to 0, the only acceleration, I do have an acceleration because it's changing direction. my acceleration is just going to be v squared over rho in the normal direction. My acceleration over here equals to v dot in the tangential direction. Both of those, again, very specific cases. You'll see forms of this. I think I do a looping plane, other things like that, which sort of follow from that. Tunk. Okay. So a simple case, or a nice case, maybe is probably a better way to put it. I have an athlete, and they're throwing a shot put, and the shot put has an initial velocity of 17 meters per second at 24 degrees above the horizontal. What are the velocity and acceleration of the shot in terms of normal and tangential components when it's at the highest point of its trajectory? What is the instantaneous radius of curvature at the shot's path when it's at the highest path of its trajectory? So remember that normal tangential components look like this. They go in towards the center of curvature and in towards the center of curvature. But the acceleration that this ball is undergoing is still g. So as it moves along this path, it's going to have nt components, but the magnitude of the acceleration doesn't change from that value of g. Oh, yeah, that's still the same. So I'm given enough information that I can write the x and y components. So the x component is just going to be 17 meters per second cos 24 degrees. And the y component is 17 sine 24 degrees, again, meters per second, traveling along this path. Acceleration of y is equal to g, and I'm just going to put it pointing downwards. It's negative in this xy coordinate system. So ay is minus 9.81 meters per second squared. And I can write Vx is equal to 15.53 meters per second. Vy at that highest point, it can't go any higher, so it has zero vertical velocity, is equal to 0. Now, the first difference you have from a Cartesian coordinate system to a normal coordinate system is that at its highest point, the normal coordinate is pointing in towards its center of curvature. So the positive direction, just one second. The positive direction here is pointing downwards. Go ahead. Always in towards the center of curvature. So in this case, I go from a negative value in order to satisfy my coordinate system in xy to a positive value to satisfy my coordinate in nt. Go ahead.
Sorry, does that say equals EF?
It equals which one? 9.81 meters per second. Oh, sorry, 9.8 meters per second squared En. Handwriting. There we go. So at this point here, which is the high point, that's g. And that's the total acceleration. There is no tangential component. And so if there's no tangential component, nothing is happening in that direction for the acceleration. There is a tangential component of velocity. So a sub n is equal to v squared over rho, which yields rho equal to v squared over a sub n. So this is a problem where the math is helpful because you can sort of see where the numbers are coming from. But the important point is really to understand that the velocity in the y direction goes to 0 at the top, that the acceleration is now limited and aligned with the y direction. So it's acting in downward vertically. And you get 24.6 meters per second, or meters for rho. So v squared is 15.53 meters per second, and gravity is 9.81 meters per second squared. Now, if the acceleration were acting in the opposite sense, pointing upward for some reason, then, or that the normal was pointing upward, it's more likely, and acceleration was pointing downward, then this would be a negative 24.6. Okay. All right, so that's not a bad one. But what happens if you look at a point somewhere along the path? Somewhere along the path, now you're going to have components of E sub n and E sub t acting on the particle. So it's the same condition. Athlete releases the shot, 17 meters per second, 24 degrees above the horizontal. What are the velocity and acceleration of the shot in terms of normal tangential components at 0.93 second, or 0.3 seconds? Use the relationship a sub n to determine the instantaneous radius of curvature of the shot's path at that time. Oh, good. So I know my xy coordinate, because ij always stays in the same direction. X is pointing positively to the right, y is pointing positively up. The tangential component is going to be the resultant of v sub x and v sub y, and it will point in the direction of v. So that purple arrow would be v e sub t of the entire system. Vy is equal to Vy naught minus gt. Vy equals Vy naught, or well, sorry. 6.92 meters per second. If you take the numbers from the previous part, 9.81 t, and you get Vy at that instant of 0.3 seconds of 3.97 meters per second. Vx is equal to 15.53 meters per second. So Vy, Vx on my figure right there. So it's climbing. It's got a positive direction up there. I can figure out at that point a number of things. I know that the magnitude of velocity speed is 16.03 meters per second. And as a result of that, I know that my answer here is 16.03 e sub t. But I don't know how to describe e sub t yet until I do the next step. Okay, well, I'm going to sort of leave that there. So if I take this same curve, I put the path down, I put the description, so now I have my xy, my vx, my vy on there. I have g, which I'll talk about in a second, but I've defined a beta. Beta gives me the angle with respect to x, or with respect to horizontal, that describes the tangential direction. Tan of beta equals Vy over Vx. Beta equals 14.35 degrees. Now, once I have that, I can rotate 90 degrees to get my E sub n. So E sub n is pointing in towards the center of curvature, so I know what the path is in this case. I can rotate down here. I know what g is doing. That's my total acceleration. If I know what g is, I also know that a sub n and a sub t have to be component parts of it. So, excuse me. So if I do that, I can take g, take cos beta, sine beta. Sine beta gives me a sub t, cos beta gives me a sub n, and I have the two component parts. Now the other thing that it's good, when I draw this out, I can see immediately that a sub n is acting in towards the center of curvature, so that's a positive value. So that's 9.5. This one is pointing in the opposite direction of the motion. And because it's pointing in the opposite sense of the motion, it's a negative value. So my tangential acceleration is minus 2.4. So acceleration in this case is now equal to this. And kind of keep it in the back of your head while you're solving these problems. It still has to describe the same total acceleration. So g sub j is the only term in the Cartesian rectilinear system, but in the ET-NT system, I now have two components of acceleration somewhere along the path. Now that wasn't the last thing I was asked for, was it? No. if I then solve through for the rest of it, I can say, look, rho is equal to a, or v squared divided by normal acceleration. I have the normal acceleration from that component at the top here. I have v squared from the previous part of the problem. These problems are complex because of the geometry. If you draw the geometry, you may find them a lot more easy to follow. So as much as possible, draw these lines as you're solving the problem to convince yourself that you're able to see the geometry of the motion. Any questions on this one? Go ahead. Yeah. So the difference between the first part of the question and the second part of the question was the first part looked at the high point. The second part took a time somewhere along the path of motion. I was given a constant acceleration, and because it's a constant acceleration, I can use this relationship, which is vy equals v naught plus 1 or plus gt, and I've put in negative, which I'm probably going to mess myself up with. Substitute in all the numbers, t is 0.3, and I get 3.97 meters per second squared, or 9.7 meters per second. Take the magnitude, just one second. Take the magnitude, and I will get 16.0. This is a projectile motion. Every one of these problems where you have a constant acceleration that's g is a projectile motion. The only thing that changes is we use bows and arrows, golf balls, baseballs. It depends, but it's basically the same thing. It's a constant acceleration problem with g as the only term. That's it exactly. In fluid mechanics later on, you'll get drag and all sorts of things, so much more fun. Okay. Any other questions on this one? Please remember, you are just describing the motion in two separate component systems. You are not changing the total velocity or acceleration. You don't care about position in this case, though. You just care about magnitude. So try and go through some of these to make sure you're comfortable with this, but particularly the geometries are the more challenging aspects, and they are the ones that screw you up on the quiz. So good luck. Thank you. Oh. Full screen. Sure.